So very good morning, dear children.
Good morning, ma'am.
Thank you for your response. Okay. So it would be very much responsive session. Okay?
Okay, ma'am.
So first I would like to request two of you to help me preparing two of my solutions that will be prepared with water. Any two. Preferably one girl and one boy.
Shall I
Come. So you put on the glass. They have their own space. Another one. So you measure 10 milliliters of distilled water from here. Ten milliliters. Is it 10 or more? Yeah. Slowly you can send it back. Yes. Okay? Yeah. So you keep that here and pour it here. No. Other way. Okay. So you again take 10 milliliters of water from here and you just screw it. Your work is to shake the whole thing until I am just explaining you whatever, and then it will take some time to dissolve. That is why I just made the solution in the very beginning. And this experiment, right? See the girl power. In one go she has prepared 10 milliliters. And you are to do. Okay. So where is the other one? Pour it here. Open it up. So you also need to shake it very nicely until I call you back. Okay? Screw it. You go to your place and shake. Okay. Meanwhile, I will tell you also. Go to your seat and shake. Okay. So our today's topic is journey to green chemistry. See, life is a journey, and chemistry is also a journey. Okay. So you see, you should ask me questions anywhere you want. Okay. This is an interactive session. So this is our art. This was supposed to be blue, but we are looking at it green because we are talking about green chemistry today, and green chemistry is a philosophy, not the color of the earth has turned green. So you have to guess what is this. Now sand. Now plastic bags. So if you see from very far away, it looks like a sand, but if you look very close, if you go very close to it, it is 60,000 plastic bags that are discarded every 5 seconds. So every time you go to shop, discard the use of plastic bags. Next, what is this? Plastic bottles. See, in one go you are just guessing the right thing. You are super intelligent children. Thank you. 2 million plastic bottles dumped every 5 minutes. What is this? This is not a picture. Another guess. Cans. See how intelligent you are. See, these are cans. Every day while returning from school, demanding from your mother, buy me 1 can. No. See, 1 million aluminium cans thrown into the garbage every 30 seconds. Only 30 seconds. So who will take care? Is only a burden on our earth, our mother earth. So green chemistry is a function of hazard and exposure. Only if we can eliminate the hazard, we don't have to worry about the exposure, isn't it? And then green chemistry, it is about preventing the pollution before it happens rather than cleaning up the mess. One question to me, to the children, is it a problem if I continue in English? No? So, have you ever heard about green geology or green astronomy or green biology or green mathematics? No? But today you are hearing about green chemistry. But before today you have also heard about green chemistry? Probably. Yes or no? But green chemistry is there. This is because only chemistry introduces new substances into the world. So that is why we have to rethink in developing chemistry in a greener way that is helpful to sustain our earth for longer days. So how we dispose our chemicals? We have to rethink. We have to reduce, reuse and recycle and definitely rethink. So there are in general 12 principles of green chemistry. I will explain a little bit of some of them. Okay. The general idea is to reduce waste materials, hazard, risk, energy, environmental impact and costs. Okay. So there will be an outline, and it actually started with the history of a woman in science, Rachel Carson. She was actually an environmentalist, she was an author, as well as she was a marine biologist. First, in 1962, she realized that in the US there had been a lot of use of a pesticide that was accumulating in the environment, that was not degraded by any organism, and that caused cancers in several human beings. And in 1970, the DDT is the pesticide. This was completely banned, and that was the first step towards green chemistry. Do you know what is the full form of DDT? Yes, students are telling me. Please tell. One of you? Yes, that badge. There. Which school you are from? I could not hear. Okay. So, very nice. So you can see that this compound, this contains 2 benzene rings, and this is very much toxic. The chains, it cannot be broken by the organisms, and this remains in the environment. The chemical factories, they produce DDT. The people, farmers, they put on the fields, and it accumulates. It doesn't break down, and it causes cancer because of its toxicity. And then there were several labs, and it slowly evolved into 1991 as green chemistry by a scientist known as Paul Anastas. point of 12 principles is the prevention. Okay, this is, what is this? This is the Niagara Falls, and there was a chemical factory near this which dumped a lot of chemicals in the canal bed. There was a school nearby, there were living habitats, and the chemicals dumped here just leaked into the domestic places, and people living there showed a lot of reactions in their body with genital defects, with other diseases. So then this chemical factory was banned, and according to one of the acts called Superfund Act, which imposed high taxes on the chemical industries, using that tax they had to repair this damage by cleaning up all the chemical waste. Again, this was in Cuyahoga River, where a chemical industry dumped a lot of chemicals in the river, and that caught fire, and this was the result. So this should be prevented. We know prevention is better than cure, so we have to prevent these kinds of things. Second is the atom economy. What is economy? We know. What is economy? We have to spend less. We have to use things in a lesser way. So atom economy is another, we have to use lesser chemicals. See, if we want to produce hydrochloric acid is a very important chemical for several industries, and then we have to use it for different other purposes. So look at this. We need to calculate a percent atom economy, and for that, you know that hydrochloric acid, it has a molecular weight of, atomic weight of chlorine plus atomic weight of hydrogen. Then we get the molecular weight of hydrochloric acid, and then this side we have the molecular weight of sodium sulfate, and this is the total molecular weight here on the right hand side. So the atom economy is the amount of hydrochloric acid divided by the total molecular weight on the right hand side into 100. This is only 34%. So if we go by this route, this is a reaction of sodium chloride with sulfuric acid, we get hydrochloric acid. The name of this reaction is, who will tell? This kind of reaction, who will tell? Anyone? Raise your hand, I will call. Yes, double displacement reaction. So if we go by this, we get only 34%. But if we react hydrogen with chlorine, we get 100%. You know how 100%? This is only the mass of the desired product is hydrochloric acid, total mass of the product, that is also hydrochloric acid. So hydrochloric acid by hydrochloric acid is 1 into 100, that is 100%. So this way we should design. But here a questions should come from you. Questions to me. Very important questions should come from you to me after looking at this reaction.
How would we get the reactants?
Please ask. How?
How would we get the reactants?
Yes, come. You come. Very big hand for him. Go back. Okay. How would we go for the hydrogen and chlorine? See, there are several reactions from which we can generate hydrogen. But the problem is how to store hydrogen. That is a very big social issue these days, because hydrogen is a clean fuel and hydrogen cannot be stored very easily. That is the biggest problem. So nowadays researchers tell us that hydrogen can be stored. After liquefying at very low temperature, What is the lowest temperature? Who will tell? Minus 273. So it is somewhere minus 250 Celsius or so. It is the liquefying temperature of hydrogen. There we can store, or else there are some solid substances which can just absorb on their surface and can store hydrogen. So these are the reactions that can give us hydrochloric acid in 100%. So we have to rethink chemistry in a cleaner way. See how clean it is now, isn't it? Another example of atom economy is this is the production of ethylene oxide, another chemically very important compound. If we go by this route, we get ethylene chloride along with some undesirable things. But if we go by this route, we get 100% atom economy. So rethink every time what can be the possible reactions. So this is another example where we have rethought and people have got prizes for that. Prizes for rethinking in a greener way. This is a ship. And have you ever thought how the ships in the ocean, they sail for days and months and years in water, and they do not get damaged by the ocean organisms. There are not only animals, there are sharks, there are biological organisms which grow on the ship hull. What is ship hull? The part that goes underwater. So that will just grow on them, eat the lower part up and make holes, and the ship will sink. So earlier people used to coat the thing with a tin compound which is very much toxic. Organisms will eat the tin compound, they will pass on in the okay.
हैंड माइक दे दो
आपका तो दे दो
Okay, so they will pass on in the water and other higher animals will eat the microbes, and that way tin will just spread. So this is very much toxic, and then the safer chemical is like this. This is an organic compound, but this is not toxic. This, how it acts is, if it is coated in the hull, the microorganisms will come to the surface, and its protein part, every organism has protein. This protein part will just get attached to the compound. It has high affinity for the protein, and the microorganism will die. But the compound will not pass on into the water. So this is a cleaner way. Have you ever thought how your clothes get cleaned in the dry cleaning? There is a chemical. People ask, there will be a chemical wash or dry wash. This is a chemical wash compound which is very much toxic. So this has been modified to liquid carbon dioxide wash. So which is not toxic. So carbon dioxide, it causes, what does it cause in the atmosphere? Pollution in what way? Global warming. But if you use liquid carbon dioxide for cleaning your clothes, it is not causing harm to the environment, but it is also not a toxic chemical. Okay, so at this point I will now stop this lecture for a small break and show you something which will just keep you entertained for a little while. Again, I want 2 more children from you, who can be from anyone, maybe from the back. 2 children, come. gloves on your right hand, another one on your left hand. You don't have specs, so you take a goggle. I want a third student, a third child. Come, anyone? Okay, come. Okay. So you hold this with one hand, one side with the gloves. You hold that side. No, okay. And you need to spray.
हेलो
So,
देखिए हम कैमरा
come in the middle. So, what is written? It's not fun. It's reverse fun. I know many of you do not find fun in chemistry. Who doesn't find fun? Yes, thank you for admitting. I know students do not find fun. So this is what, and I would also like to know from you who is there who can guess what are the chemicals present here and what he has sprayed. Though the color is similar to copper sulfate, but it is not copper sulfate. Can you place it on the table once? Okay, I will show you the reaction in my last slide. And another one, you also hold it here, you place that here, and you need to take this and pour the solution inside that. Close it. And spray. You need to spray it on the written part. It is written green, and what is the color? Yellow. And he is spraying something on it. And show it to your friends now. It's okay. It's enough. What is the color now? Green. Okay. So you keep it here. Thank you for showing your friends, and these are for you. Oh, first open the So the first reaction that changed colorless to some color, that is a very common reaction that maybe some higher class children may be doing in their practical classes, that I will be showing in the last slide. But the second one that changed the color orange to green is something very interesting. So that first you need to know what the orange color was. That was actually a potassium dichromate solution, which is orange in color, isn't it?
Potassium?
Dichromate.
Potassium dichromate.
Dichromate is the solution And then who will tell me what is the oxidation state of chromium in potassium dichromate? Come. He is very prompt. Thank you. Okay. And then when it turns to green, chromium cannot change to any other element because I haven't done any nuclear reaction. It has only converted its oxidation state, which is green in color. What is that? Raise your hand and tell. Not 4, but not 2. 3. Who said 3? Come. Who said 3? See, actually, the thing is that chromium dichromate is very, very toxic. And industries, they use dichromate for several purposes, and it is so toxic, so mobile in the environment that it can cause destruction to even human cells. And the reason is very obvious. You see, it is highly oxidizing. That means it can oxidize living cells also. That causes damage. So, people can change from toxic chromium 6 to chromium 3 very easily using some reducing agent that can supply some electrons to it. For that, we can use very conventional reducing agents, stannous chloride, zinc, hydrochloric acid, like that, but we have not used for that purpose also. We are reducing chromium 6 to chromium 3, toxic to non-toxic, that is also a green chemistry. We are not using the substances stannous chloride which are even toxic. Tin, you have seen, tin was toxic. We are not using tin, but you are using something. That guy has poured something here that was not containing any toxic chemical. That was, can you guess? That was only vitamin C. You can get it from a medical shop if you get cold. Ascorbic acid, we call it in chemistry language, and that has the capacity to convert chromium 6 to chromium 3. See how we can rethink and reduce the use of toxic chemicals. Okay, so now we come back to our main topic. We can use safer solvents wherever necessary, like water. People have used several organic solvents like benzene, chloroform, pyridine, which give very toxic smell. They are volatile. If you go very close to them, they smell very bad. That means gases of that, they enter in your inhalation system, which is not good for the health. So it is toxic. But we have to replace those solvents into safer solvents. Mostly water, there can be others also, but water is the best one. So, in our analytical chemistry, we have the solvent extraction systems to separate one chemical of high importance from several other chemicals, and for that we use the separatory funnel containing an organic solvent and water, wherein we separate the sample of interest in the organic solvent phase. But that is toxic handling of organic solvents. That is now replaced by water solvents. My friends are mixing here two solutions. Your hands are aching, my dear. Come. The solutions are prepared. Solutions are done? Almost. Okay. So let them stand for some time. Yes. Okay. So the rest part will dissolve upon standing. Let them take test. Watch. What you see. Gloves also you can have. No, you keep that. After some time I will again call you. Keep that. Keep that with you. Okay. So we can prepare two water solutions. I will just mix them and show you. If you mix two water solutions, they will not mix with each other and they will just show you two phases. It is very a common perception that if you mix two water solutions, they will just mix with each other. But if you know which two solutions do not mix, then you can use this idea to separate your sample of interest. You can just use this idea to replace this old concept of organic and water systems for separation. Just rethink. Okay. And this we can learn from nature actually. If you go to some parts of, okay, this is not the thing. You know, this is our own Madam Marie Curie, and there had been a lot of work by Madam Marie Curie in separating uranium and two other elements from radium and polonium from pitchblende, which is the mainly uranium ore. And this is Madam Curie with her electrometer, which she used for studying the radioactivity in different samples. And this is the pitchblende, actually raw pitchblende from which uranium was recovered. And then actually radioactivity, it was first, phenomenon was first observed by, not by Madame Marie Curie, Henry Becquerel. Who says this? Two of you come. Come. You're from which school? Okay. You? Okay. Thank you. So, Henry Becquerel first observed the phenomenon of radioactivity. That was an accidental discovery, but the name radioactivity was given by Madame Marie Curie, and actually Henry Becquerel was the PhD guide of Madame Marie Curie, and the whole PhD thesis of Madame Curie was on the phenomenon of radioactivity, which subsequently gave her the Nobel Award in the year 1903. And that was an additional thing because at that time Irene Curie was very small. She was born in 1897, and you can imagine how small she was when her mother was awarded the first Nobel Prize. And in 1904, Irene got a little sister who can you name? You know her name? Eve Curie. And at that time, Mary was also continuing her research with the uranium ore. With that, she found, at that time only uranium and thorium were known as radioactive substances. But Madame Curie was continuing her research with her PhD supervisor, Henry Becquerel, her husband, Pierre Curie, and they found another radioactive element, that was polonium, which was having much higher radioactivity than uranium, and the next one was polonium, and the next one was radium, which was even higher radioactivity. Okay, so polonium and radium, these were the two substances newly found in the uranium ore, which were having much higher activity than uranium. Polonium was named on the motherland of Madame Curie. So this is the radium, shows activity in the dark, and she was handling so much of activity, and nowadays a small amount of this is used for the treatment of cancer. Even the second Nobel Prize, which year it was given to her? 1911. The first one, 1903. Second one, 1911. First child, 1897. Second child, 1904. So working woman scientist with two small children, not a matter of joke. And the Irene was also working with synthesizing artificial radioactivity, which has even higher impact in curing cancers. Okay, so that has just given birth to a completely new era, which was just given as a gift to Madame Curie and her family. So you can see the photograph where so many Nobel laureates are present. You can identify. In the row, I don't know how many you can see. See, there are so many Nobel laureates. Heisenberg, then Debye, then Bragg, then you have Langmuir, then you have Max Planck, and then you have, I don't know how many names you have heard, Pauli. Out of so many Nobel laureates, only the first lady to have the Nobel Prize of two subjects, two Nobel Prizes, the first lady to be the woman professor at the Sorbonne National Laboratory of France, which did not admit her as a student because she was a lady. So this was a great achievement on her part. Now, the organic solvent, coming back to this, and the aqueous system, because Marie Curie handled a lot of radioactive substances to separate radium and polonium. She also handled a lot of organic solvents to use the extraction phenomenon, for the extraction phenomenon. So it was not a matter of joke to handle so much chemically as well as radioactivity containing toxic substances. So now you can see that how we learn from nature. We see that in certain parts of sea and ocean and ocean, where they meet, they show a distinct separation line. Can you tell what makes them separate?
Density.
Only density, and there is one more phenomenon. The salt. Because the salt that comes in contact with high salinity, they just agglomerate, they just aggregate and separate. So that is the line of distinction, and here also we find the same thing. The two solutions the two children were preparing for me, one was of sodium sulfate, a salt, another was of a water soluble polymer that is called polyethylene glycol, which is not like the polymers we use normally, the polyethylene bag, not like that, because this polyethylene glycol is used as a drug delivery agent. The capsules in toothpaste, in every biocompatible, which is biologically safe, we use this polymer which is water soluble. So now come two of you with gloves. So one of you take this and you take, doesn't matter. Now both of them are same. You just pour little bit of solution from there. Okay. And now keep that. Yes, okay. Now see, the one that you had poured first has now lifted upward. That is because of density. So that we can use for solvent extraction. This solution, you know what is this? This is just a solution prepared from turmeric powder that we use in kitchen, and that is dissolved in alcohol and filtered out. This is just that solution for used for cooking. Okay, so I will just use it to show how this solution has preference for only one phase.
Sir, kindly sit and take the photograph.
Can you add this a little bit into it? See, the yellow part is where? On the top or top? You see where it is? Yes. So the white portion of the polymer solution is containing the turmeric. So this is just to show you by color, but if it does not contain any color, but if you put it in any kind of instrument that will check it for you whether that element is there or not, you can see that that particular element has preference. Either it will shift to the top or it can go to the bottom. So we can very easily attain the biphasic system, not with organic solvents but with water soluble substances. Okay. Thank you for helping me so much, and for that you get chocolates. You open the glass first. You get chocolates, and you also get reward points because you got your hand aching. Thank you. Okay, so we carry on. This was the biphase. Okay. So next point in the towards the journey of green chemistry is the use of less energy. We use heating on some heating source, gas oven. But if we use gas oven or a heater, then there is a process of convection, conduction and radiation, which only gives heating from one direction. But if you use microwave, why the heating is so fast? Because heating is from all directions. So we are using less energy by that. Then if we use renewable feedstock. Renewable means which can be used over and over again, and feedstock is what? Which is coming from some biological sources. See, we have corn. We eat corn, but we can also use it for making some substances which are normally made from plastic. We have some chemical processes that can be converted to polylactic acid, PLA, polylactic acid, and that nowadays we use these kinds of spoon and fork whenever we bring some food from outside. These kind of spoon and fork are coming, but we are not getting the normal plastic spoon that we were using some 2-3 years back. So these are the reactions, and then we are not doing preparation of derivatives, more and more reaction steps that are involving more and more chemicals. That is also a step towards the journey of green chemistry. Then use of catalyst. What is catalyst? Yes, a substance which accelerates the reaction, which helps in the formation of products in some other pathway, in some other route that involves lesser energy. So catalyst is also towards green chemistry. Then we design some methods that will help us degrade the products that we have produced. So after the use, everything should be degraded. We not only that we produce, we also degrade. So the polylactic acid that is easily degradable, so it should be produced very safely. Then is the real-time analysis. What is real-time analysis? While cooking, chemistry is very close to cooking. Do you agree? Yes. So while cooking, we always do real-time analysis. We put something to cook, we go and check whether it is boiled, whether the cooking is done. So reactions should also be done. It should be checked whether it is complete or not. Otherwise, we set it for 10 hours and go to sleep is not green chemistry. Otherwise, there will be unnecessary use of energy and chemical reagents. So this is how real-time analysis should be done. Then inherently safer chemistry methods should be developed to avoid accidents including release, explosion and fires. Now at this moment I come almost close to the end of this today's session. So you have to identify now which are the reactions that is close to green chemistry. Okay. See, in reaction A, we have, these are the reactants. B, see how fast you are. This one is also B. Okay. This one, A. This one, okay. And this one, DDT. Okay. So thank you so much for answering these questions, and you get double reward points if you think green, and thank you for your attention.
The reactions of those two perfections.
Yes.
Color change.
Yes. Here you are.
So students, if you have any questions, you can ask ma'am. So any questions? Anybody?
This one is the blue thing you have seen in the C part, Y part. Do you know which blue is this? Blue has several names. Which blue is this? This is a simple answer. Prussian blue. And why this is called Prussian blue? That is also simple answer. Anything to do with Russia? Yes. Something to do with Russia. See, in the olden times, Germany, Poland and Russia were considered under the same country. And the soldiers of that country wore this blue colored dress. So this is called Prussian blue. And this complex is red, blood red color we call. Iron thiocyanate complex, and this is ferrosoferric sand. Okay. Anything else that you want to ask?
Students, any questions you want to ask? Anybody? Well, thank you, ma'am, for your wonderful presentation.
Thank you. Thank you very much. Thank you, children, for your attention and for just reacting, interacting and responding with me and making the session very successful. And those students who do not find fun in chemistry, did you find fun in this particular session?
Yes, sir.
Thank you so much.